Video will have an awkward beginning where it's clear that I've left off recording. Um, so anyway, we're going to be doing Project P1B. Project P1B is a world switch, meaning instead of programming in the nice, friendly world of Linux, where in user programs where everything is nice, and when you do something wrong, it's actually just like a little bug in your program. This is like the best thing in the world. When you use a computer, you aren't worried it's going to blow up, or you're going to hang it, or stuff's going to break irreparably. Now we are going to switch into the world of kernel development and do a little bit of an initial kernel project. The kernel project is a very simple introduction to the XV6 kernel. Like I said last time, for those of you who missed it or didn't hear, we're working on this little kernel called XV6. It's a port of an early, beautiful little version of Unix called System v6. Unix has this great history going back to the late 60s and early 70s when it was developed, and many different versions over time as it became a real operating system. It almost kind of disappeared for a while as each company took it and made their own versions, and all these lawsuits happened. And then fortunately, Linux came along and kind of actually took over the world in a lot of ways, and also reinvigorated CS research in operating systems, which I'm personally grateful for. So in any case, Unix is great history, and this little kernel we're going to be looking at is a little Unix kernel. It's not very big, but it's a real kernel. You can boot a system on it, and it does just enough stuff so that you can understand all the key parts of CPU virtualization, memory virtualization, file systems, how concurrency works. All the things we're going to talk about we'll see forms of inside of that kernel. Now, these projects are much different than the Linux projects. Some people will have this opinion of the XV6 projects at the end. I hated those XV6 projects. That will be some of you. To those of you, I apologize. Some others of you will be like, oh, those were really interesting. That's what I liked most of the class, is getting to work in this little kernel. I'm trying to get it so that everybody's like, oh, I really at least understood why we did that, but you still may not like it. It's different because you tend to spend a lot of time understanding code that you didn't write. This is, by the way, probably a more important skill than being able to write code, is to be able to understand other people's code. Because what are you going to do when you go off and work? The first day you go and work at some company, you check out some code base, and they say, hey, can you add this feature or whatever? And then you have to do it. It's not like you normally are just writing main programs from scratch. That's an uncommon situation. So learning to read code is a skill. We kind of do it by osmosis here. We give you a big code base, we walk you through pieces of it, and we go from there. So hopefully you'll have fun with that. That'll be due again in about just under a week, which you're excited about, I can tell. But it's really like 6 lines of code, okay, which I basically show you all those 6 lines of code. It's just, how do I work with XV6? How do I build it? How do I edit things? How do I start learning about it? How do I turn it in? It's a little different. And we'll have tests again for that. So we have, of course, discussion, which talks about that. This week we're going to do it a little differently, and I'll do this just probably a handful of times, a few times in the semester. I have already recorded a beautiful discussion video about how to intro to XV6. I watched it, and I'm like, I will never do it that well again. So instead of forcing you to come here tomorrow and have me create a lackluster facsimile of that previous video, I'm just going to encourage you to watch that video and us not have discussion tomorrow. So now your week is free. You should be able to do all sorts of things this week that you weren't able to do before. So I'll put that on the webpage. I'll send mail about it. Still 4 of you will show up here. If that's cool, hang out, watch the video together. I will not be here tomorrow, okay? So sorry. But we'll do that just a couple times. I mean, I like discussions. Actually, I love, plugging in the laptop and getting to do a little bit of code with you. So I generally will do that, and that's why I like running discussions. But just a couple times, I'm like, I already have something that's perfectly good. Why not just let you watch it on your own time? So that's that. We will also soon then have the TAs will grade P1A, and we'll make those grades available. And the thing when we make the grades available for you to do is to see if there's a discrepancy between what you thought you were going to get and what you actually got. Can you guys quiet down a little bit, please, over there? Thanks. So in any case, please check that. I'll send mail about that when that happens, and we'll go from there. So any questions about that? Okay, oh yes. we'll just dump it into your hand-in directory, and and then I'll send emails saying this is the file you should look at. Yeah. Another thing, we did a vote, a Piazza vote. The results are in. Oh, more than 200 people voted, and what percent wanted there to be Piazza? Who's going to guess? What percent? Not 100. We heard 60-40. That's wrong. We heard 95. That's close. It was about 91% want Piazza. So therefore, we're going to do it. It had to be 96%, otherwise we don't do it. No. So therefore, I will do that. I've already started doing that. I think a bunch of you signed up already, even though I didn't do anything yet. I'll be spending time with it tomorrow, and the TAs are familiar with it. So we're going to transition a bunch of stuff over to there for questioning. We'll still keep the email list for if you have other questions or you don't want to somehow do a private note through Piazza, but we'll generally try to use Piazza as our medium for questions about projects. We'll see how it goes. You all like it. I don't know anything about it. The TAs seem to think it was okay. So between those three things, I guess it's worth trying. We'll see how it goes. I was told, for those of you who are not familiar with it or are just really bad at it, the one thing you should, of course, be very careful with is you can create public posts or private posts, private or public questions. When you're sharing any code, please do not make a public post about your code. You can ask generic questions about anything, of course, in public. But if you have a question about your code, either use the email address that, as we already have, or do a private post on Piazza, and we'll try to get to those. Okay, so we'll see how that goes. Thank you for participating in this democratic approach to Piazza decisions. So that's what we're going to do. Okay, so one last thing. Somebody asked me about, sometimes this is kind of a generic thing about class. Sometimes I get asked, like, why do I want people to come to class? And sometimes you kind of get the view as a student, like that I'm giving this class and you're just sitting there. But I wanted to just say, first of all, like why it's important to me for you to come to class, just so you have some sense of that, even though we're recording everything. And so you can hear this delightful discussion later if you don't come. And for me, it's a lot about why coming to class is fun is because people are here. I have tried to record these videos like this by myself. And I should actually just give you two as a contrast so you can see how badly they go when I'm talking to myself. It's just nothing enjoyable about talking to a computer. It's talking to people that makes it enjoyable. And the other side of this class that I'd like to say why it's important that you're here is that all the material you see has been shaped by essentially previous generations of you, right? Like when you explain something in class as a teacher, you see what things people don't understand, and that shapes how you teach it the next time. You make it better. It's just constantly a refinement process. And even the most basic things, like how I talk about CPU virtualization, have been shaped by many, many questions by people just like yourselves in this hall, or different halls. They used to be much smaller halls, actually, which was a different experience entirely. But that certainly shapes the future, is how we interact right now. Even the OS book that we use, which is just our own book, as you know, created from notes, all started because one student came to class and asked me, can we create something like this? And it wouldn't exist without students pushing for it and then continually actually giving me positive encouragement about it. That's why the OS book exists. So anyway, that just question comes up sometimes. Why should I come to class even though I can just watch the recording? Is it because it's more fun for me, but also it just makes for a better class both now and in the future? So that's your randomly programmed come to class note. I will do other things to try to get you to come to class too. And also it's nighttime. Like, what else are you going to be doing on a Tuesday night? You're probably like, is it time? I mean, you might be wondering on the weekends, can I go to OS class maybe Friday night, Saturday night? If you want, we could think about switching to one of those nights, but maybe not. We already have office hours with TAs on Friday, so that why would we definitely already have plenty of time in OS class. Tuesday night here, and then Friday through Mondays with the TAs. Oh, there's, by the way, one other poll, which maybe will be the first Piazza poll that we do. We will ask when you want help hours from TAs. So we will just ask you that, and we'll do kind of a distribution. So please do vote on that if you care when the TAs are available. Okay. Any questions? Okay, so let's finish our discussion of CPU virtualization, the mechanism side, and then what we're going to do for the rest of the class, we're going to do essentially one more lecture right here, which will be, I'll call it hour 2, about mechanisms, and we'll start talking about policies. And then the last little bit of class, instead of me talking, we will look at some of the chapters have homeworks at the end of them, and we will just do a few of them together. So we'll kind of change pace, and you can talk with your friends as you solve some problems together. I'll show you what that means in a minute. But this way, I don't have to ask you to just look at the homeworks on your own. I can kind of force you in class to do it. And it also will get us through hour 3 in a different way other than me talking a lot. I do like talking, as you might have noticed. But I don't like talking that much. And by hour 3, you probably don't like me talking that much. So we'll try the homework angle as a way that you can learn about what those homeworks are without even doing them on your own, which is maybe a good thing. Okay, so we have some basic idea of these mechanisms. We have user and kernel mode. We have a way of transitioning between them. We have timer interrupts to allow us to regain control of the system and so forth. We have to do a little more now in the OS in order to, as we add more functionality, the OS is going to have to do more in software. And one thing it's going to have to do, it must track the different user processes in the system and what they're up to at a given point in time. So that's a new responsibility for the kernel or the OS. And what this is often is some sort of data structure, which we'll just call a process list. Historically, it was just like a simple list or an array, as we'll see in XV6, that kernel. That could, of course, be any data structure that tracks what processes are in the system. And you can think of each element on this list as having a lot of per process information. Things like, the name of the process, like a process identifier. It might have just different elements like what files it has open. And it also has something which we'll call the state of the running process. So, for example, in our example that we looked at earlier, remember A was running, and B was over here kind of waiting to run, ready to run, but it wasn't running. And so in this mode right here, we would say that A is running and that B is ready to run. So we're going to track that kind of the state of the process with those two terms, ready or running. And on any CPU, of course, at one time we might imagine on a busy system that there's one process running, and there may be many processes that are ready to run but not running. They're suspended. We're waiting to run them when a CPU becomes available as per our policy. So just the important things there to remember, we have some sort of process list. We'll see this in XV6. We'll take a peek at this in some detail. We'll see this in the future. But just that the OS is kind of paying attention to this, so that when it is interrupted by the timer, it can look through a list and say, oh, I've noticed, for example, that this process hasn't run very much. Now I'm going to run it, and then suspend this other one for a while. Okay, but these states aren't everything. There's another state that we want to think about with a running process. And that all relates to what we called last time, what we called problem number 3 in CPU virtualization, which is that some operations are slow, particularly like I/O. Input-output to a device like a disk or an SSD even is way, way slower than the processor. Or processor speed, super fast, billions of instructions per second. A hard drive, hundreds of operations per second. Billions of operations per second from the CPU. Hard drive, hundreds of operations per second. It's just a huge gap. And that's why, of course, finally SSDs have come in, and they're in the, say, tens of thousands of operations, or maybe 100,000 operations per second. Still not nearly as fast as a processor, but much faster than a hard drive. We'll talk more about persistent storage devices later on. But we need something to do, and the OS needs to think about a little bit what to do when slow operations occur. So let's say A is running along. It wants to do an I/O. So what does it do? It issues a trap And this is part of a system call that is to, say, read from the disk. It traps down into the OS. And then the OS, let's say we have our hard drive here, issues a request. The OS runs a little bit, and then it issues a request I/O to, say, the disk. And then the disk runs for 10 milliseconds doing this. Now, if this is a few instructions, 10 milliseconds would be represented by, well, I'd be doing this a long time. How long should I do it? Like a long time. Okay. It would take a long time. I don't have enough virtual paper to express how long 10 milliseconds is if this were how long instructions took, because 10 milliseconds is forever. What it means is when the OS issues this I/O, it doesn't want to just sit around and wait. It means we want to do something else. In fact, naturally the thing to do would be, okay, we issue the I/O to disk, we kind of wrap up this calling, and then maybe we run process B now, right? We return from trap into B, and B runs. And if B is running, that means B is using the CPU, and it means we're getting better utilization out of the system. So this generic idea, and I'm going to erase all these lines now because that wasn't as insightful as I was hoping for. But yes, this I/O is going on for some time. What this allows is better utilization of the CPU. And it's a very general principle. In a concurrent system, we're overlapping a bunch of activities. You can see how the OS is kind of juggling all these different processes, trying to get the most use out of the CPU and make things run more quickly and make sure the disk is busy, make sure the CPUs are busy, whatever. Trying to keep everything busy, because if we're keeping things busy, generally, we're kind of making more progress. Now, amazingly, that's not always true. And maybe we'll talk about this a little bit later, but there are times where it's actually better to wait and not do something, and it'll actually make the system more efficient. When is that? When can you think of things like that? When is it sometimes better just to wait, and then actually it causes you to do less work and you become more efficient? I mean, you must have this experience through Piazza. You wait till all the eager people iron out all the bugs of the project, and then you come in late and just do the minimal possible to pass the test, and then you're done, right? You waited. You weren't utilizing yourself that well, but you were more efficient in the end because you waited. That happens all the time, actually, in computer systems too. We'll talk about that throughout. But generally, we're trying to use the resources that we have. We have CPU, we have, like in this case, a disk, and we're trying to overlap. So to do this, the OS is going to, this is kind of a full, what we call a multi-programmed OS. It has another state that we're thinking about. So the states that we talked about that the OS are tracking is, we talked about ready, which means you could be running on the CPU, but you're not. Running, which means you are running on the CPU. And then now we have a new state which is called blocked, or blocked on an I/O. And that means let's say process A in our example here has issued an I/O, and then it moves to the blocked on I/O state. And it will not continue, it will not become ready to run again until the I/O is complete. We can't keep running because we need that data from the disk in order to make progress. So you can think of this as like a state diagram. Let me just draw it right here. A process can be running, it can be ready, it can be blocked on I/O, blocked. That's not how you spell blocked. So it can be in any one of these three states. Going from ready to running, we call that getting scheduled. Going from running back to ready, we call that getting descheduled. Going from running to blocked means you essentially issued an I/O, right? So you called into the kernel and then issued an I/O request to, say, a slow device of some kind. And then when the I/O is done, then the kernel the OS moves you back from blocked into a ready state, and at that point you may be scheduled again, maybe immediately or maybe later on. And so that's kind of a common transition. There's also a few other states that we sometimes think about, like an initial state when the process is being created, and then after you get killed, after you've been running, sometimes there's a state called the zombie state, where you're kind of dead, but you're not yet cleaned up. We'll see where the zombie state occurs when we think a little bit more about a process, building our own process scheduler. So this is just a kind of a new thing that the OS has to do. OS tracks all these things, and the goal again is efficiency, just efficient use of resources. Using the CPU, keeping it busy, not sitting around and waiting for slow things to happen. And this goes, again, way back to the earliest operating systems, right? You had a mainframe, it was an expensive computer. You didn't want the CPU to sit there while a program was waiting for something to happen, so you switched in something else and started running it. It goes back to the, really the 1960s or even the late 50s. Very earliest computer systems, people saw this problem and started to build OS support, even before it was called an OS. Some people called it different things, actually. I think OS ended up being kind of a good name. There was also like Master Control Program, which sounds sinister and actually is like the evil character in the Tron movies. That's also an early kind of name for the OS. I'm sure there are lots of other names that we could have thought about, but basically OS and kernel stuff. Okay, so any questions about that? Hopefully you have an idea now of the mechanism of how the operating system virtualizes the CPU in conjunction with the hardware works now. You should have a sense of the OS boots up, it sets some stuff up to make sure that, yes, it's in kernel mode, it can do whatever it wants, but it wants to make sure when it runs user programs that they're not able to do that. And then it transfers control in this very specific way to user programs who can then execute efficiently most of the time, but once in a while the OS has to get involved again, and the hardware makes sure that those user programs can't do anything unexpected. We call that general protocol, so the summary here, we call that general protocol limited direct execution. And it's the core of every real operating system that's out there. It's basically these sandbox environments that you create for user programs so that they run quickly, but they can't do everything that they want. That's that limitation, right? This is the security side of this, and this is the efficiency side. Security and efficiency, two important goals for any modern operating system. Okay, so if that's that, then we have one more lecture piece to talk about today, which is we are going to go from mechanisms up to policies. Then I'll just kind of introduce this. I'm going a little bit slower than the very aggressive schedule that I had put down. The day one of class for me is I imagine we will learn 10,000 things, and then the reality comes in that I need to go at a certain pace, which is always slower than what I perhaps my ideal is. And so we'll go a little bit slower, and I'll adjust the schedule on the web page as is fit. So don't worry about that. I'll figure it out. And part of the reason, of course, we try to cram so much into class is, like I said, I think probably the first day, there's so much to know. When you're trying to understand the huge systems of the world, there's so much to know. And here we're just getting the first real sense of one complex system, the operating system. To understand large-scale distributed systems, you have to understand operating systems. And even understanding an operating system, we get just a bare introduction to that here. So that's why we're trying to cram so much in, but we don't want to cram so much in that, you hate your life and me and this room and the smell of this room and, just everything about this building. We don't want you to have that sort of, stress reaction to operating systems. So I'm trying to balance the right amount. Of course, you can give feedback on that. And maybe we'll ask maybe we'll do a Piazza poll. I'm getting very excited by Piazza. I've completely flipped on it from hating it to now loving it. And we'll ask you probably about a month in about the pace of things, lecture, projects, etc. And you'll have a chance to steer that as well. And of course, you have to always take into account, you're in a big class, which means some people could go very fast, some people will be average, some people would be great if we could review more. Some people have transferred here from other universities. Some people are graduate students who had a completely different undergrad education. Some people are, 14 years old or whatever. So there's a whole range of people in here, and we all have to understand that we kind of have to travel at an average rate. So I'll be sampling you to try to kind of maximize that rate, or maximize the satisfaction from the rate that we go at. And so, of course, please be forgiving of us if we're going slower than you want, and please try to work more if we're going faster, I guess is the result. So anyway, as you notice, I tend to get sidetracked. The only negative is for me is that I'm recording this constantly, and my sidetracks will be, as I said, immortalized. And what is going to happen to YouTube videos at 100 years from now? Like, what are they going to do with all those videos? Are they just going to start deleting them at some point? Who knows? This is a question for us. We will wonder about this. YouTube in 100 years. What's going to happen to this video? Is anyone listening? I guess is the question that I'll ask right here. Is anyone listening? Somebody will find this, and it'll be dramatic when this happens in the year 2118. Wow. Wow. Won't that be awesome? That'll be so great. Someone will be like, can you believe they looked ahead and they saw the future? What did we see? Let's do a few predictions of the future. What will we see in 2118 for the people that watch this video? Of course, flying cars. This is always in the future, so we should predict this. What will we see? What else? I don't even know what that means. Yes.
They're not watching on the screen.
They're watching on their brain. Yes. On your brain. That's awesome. That's probably true. What else? Yes. They're watching on Mars. On your brain on Mars. Wow. What else?
Self-driving flying cars.
That's never going to happen. No, forget that. Who thinks self-driving cars are going to happen in the next 5 years? Yeah. So you've all bought into this hype. This is not going to happen in the next 5 years. I mean, they'll start doing it, and then they're all going to start crashing because they feel like, hey, I didn't know it snows in Wisconsin. I didn't know that roads could be icy. This is a very hard problem. What they'll do is it'll all be like driver assist, because it'll be like on the highway, it'll be like, and you'll wake up. That part will work. The full driving, I don't buy it for the next, I don't know how many years. Anyway, so maybe on that. Maybe self-driving. Self-flying. All right. Cars. Maybe. All right. And what else? One last prediction? No, I don't want AI to control them. I like programming. Sorry? What? Oh, like instant translation. That would be awesome. So no longer do you have to learn anything. Instant language translation. Yoga for AI. Okay. Let's stop on that one. Yeah, I'm actually quite worried for my own profession, because if we really do invent like a general intelligence. Sorry, this future discussion is too exciting for everybody. Just think, though, you'll be part of this in the future. Someone will listen to this, and it'll be awesome. So anyway, the future, though, for me is like, will there be teachers? If there really is an intelligent thing that you can talk to, if that's possible. Like, you'll just have like a personal teacher that you can ask any question. You will not have me anymore. Now, my hope is that someone watches this video and then programs my personality into that thing, so then everybody can be my personal student. So, future is Ramsey is everyone's teacher. That's my hope for the future. Okay, this is not going to happen. All right, back to the very related topic of OS scheduling policies. Let's transition. Sorry, everyone starts chattering too much and then I can't think properly. So let's skip all of that and come try this again. OS policy. So we have now a very simple thing we're going to do, which is we have a mechanism which allows us, when A and B are able to run, we can run A for a while, then B, then A, then B. Or we could, for example, instead we could run A for a long while, and then we could run B for a long while. We have the ability to do that. That's what that mechanism does. We have the conceptual understanding of that mechanism. We don't know exactly how it works on the hardware, but we'll look at that. When we look at the x86 kernel, that's a real OS kernel, you'll see exactly how that's done. So this is the mechanism, the how. But now we already have that, so check. But now we have like the what. What should we do? What? 2 question marks. What should we do? Should we run A? Should we run B? So what we're going to just do in the next, let's call it 20 minutes, half an hour, is develop our intuition around that. We won't solve the problem quite today. Like I said, I'm going to go a little slower, and then I'll update the webpage as need be. So let's develop our intuition. So to do this, the first thing is we're going to have to make some assumptions. And what we're thinking about here is basically what do we have to know in order to make this decision intelligently about whether to run A or B, or A, B, or C, or whatever. And so we're going to make a bunch of assumptions, and we're going to call each running program or each process, we tend to call it a job. This goes back to the fact that people thought about scheduling of work long before operating system schedulers were even built. People were building, factory automation, and they were thinking about like how to schedule work in a factory. And so the theory behind all of this stuff started before computer systems actually cared about it. And we've borrowed some of the things they think about, and we've borrowed some of the terminology that they use. And that's why you'll see this kind of sometimes different words. Even though when we say a running program or a process, that should be enough. But we'll also just call them jobs, because historically that's what the scheduling research literature does. So we have to make assumptions about these jobs and their nature in order to do a good job of scheduling them. If we don't know anything about what programs we're running, it would be very hard to know what's good or bad. So we're going to make a bunch of assumptions. And I'm just going to write these down. They are basically what we'll do is we'll make a bunch of assumptions, and then we'll try to remove the assumptions as we go to make a more general purpose kind of scheduling policy. So here we're going to assume something, and most of these assumptions are unrealistic. So we have some sort of set of jobs, and they all arrive into the system, so they're all created at the same time. Okay? So this is clearly not realistic. You run programs all the time throughout the day when you're using a computer. You don't create all the jobs at once and say, okay, computer, schedule these, and I will never ask you for anything again. That's not realistic. But for simplicity, we'll assume that at the beginning. We'll also assume that each job only uses the CPU. So for now, we're not worried about, say, I/O. We're also going to assume that each job runs for the same amount of time. That's clearly not realistic. Some processes you run finish very quickly, some finish very slowly. So that's not realistic, but we'll assume that at the beginning. We're going to assume that, let's call it some time t, okay? T sub I, perhaps one for each job, but they're all the same. We're going to assume that T sub I is the same for all, so this is some amount of time, T, and then that Ti is the same for all processes. So they run for some amount of time, it's the same length of time, and so I guess I'm saying the same thing here. Let me just do this more carefully. And this is known ahead of time. Sorry, a little bit confusing there. We'll clean that up in the post-processing. No, we won't. So in any case, we know how long the jobs run. They all come in the same system at the same time. They all run for the same length of time, and we know exactly how long they're going to run for. Now, we don't generally know that, right? We don't generally know how long a job runs for. When you type something at the command line, how often do you know how long it's going to take? Sometimes it's instantaneous. Sometimes it takes hours. What does it depend on? What things does it depend on, like the length of a running program? Like if you wanted to predict it, like a particular program, how long it was going to take, what would you ask about the program? One, nothing, and you just guess, yes. Oh, sorry. The time could be, so you might ask, hey, is there some algorithm in there, and does it have some sort of particular complexity with respect to the data? Yeah, in the very back. How much memory does it use? And for example, do we have that much memory available? Yeah. Does it do a lot of I/O or not? Yeah. yeah, something about the code size, how big the code is, what it's doing. I mean, you could ask so many questions, and it would still be very hard to predict things about it, right? You could maybe come up with some heuristics. It's very hard to know anything about program runtime. It turns out that it's important for scheduling to know runtime. We'll see why that is. So at first we're going to assume that we know it. Then when we build the most realistic scheduler, we're going to assume that, of course, we don't know it, and we'll try to learn something about it. Okay, let me just fit these all into one screen. We're going to assume one last thing, that there's a metric that we care about. A metric is something that we can, obviously, by the nature of the word, is something we can measure, and it's something that we are going to use to determine, is one policy better or worse than the other. If we don't have a metric, we're just going to compare them qualitatively. We want to be more quantitative, so we need a metric that says, hey, this policy did X, this policy did Y, X is better than Y, therefore this policy is better. The metric we're going to use at first is this classic metric called turnaround time. It's simply the time that the job ended minus the time that it arrived in the system. Okay? So very simple, or you could say when the job completed versus when it arrived. So let's do some examples. So let's try to remember all these. Unfortunately, this is where the setup isn't quite perfect. Like on the chalkboard, I could leave it up. Here, you're just going to have to kind of remember it, or we'll just kind of keep going back and forth to it. So let's do an example. Let's say here's an example. Let's say we have jobs A, B, and C. They all arrive at the same time because we said they were going to at t equals 0. They all have a run time of, let's say, I don't know, 100 time units. Doesn't really matter what they are. And I guess everything else that we say is true. They only use a CPU. We already said they run for some amount of time t, and that's same for all. And that all we care about is turnaround time. So let's go ahead and show what the turnaround time is. These get scheduled, and to schedule them, we're going to start using some different policies, or what we might call algorithms. The first algorithm that we're going to use is the most basic algorithm that you would come up with, which some people will call FIFO, or first in, first out. Sometimes it's also called, aka also known as, first come, first serve. Same thing. So I'll just write that out here. First come, first served. FIFO scheduling is the fundamental thing in American institutions, right? When you go to the theater, when you go to a restaurant, you expect there to be a FIFO ordering. When someone tries to break the FIFO ordering, you get very angry because that's just how we do things, right? You expect things to be in FIFO order. So we could also build a FIFO scheduler so that processes don't get angry at each other. That would be a perfectly fine thing to do. What of course we're going to see is that FIFO schedules don't have some properties which aren't so great, which we'll talk about more in a second. So, I mean, it's even kind of weird to think about FIFO when I already said all the processes arrive at the same time. So there is no first one. But let's just pretend failing that they arrive. If they arrive at the same time, then we'll just kind of pick alphabetical order. So our policy will run A, then B, and then C. And what we'll do is, at first, we will just do something called run to completion. So we know we have the ability to switch between processes, but at first we won't do that. We'll just run to completion. So when we run A, we're going to run till it's done, then we're going to run B, run till it's done, and then run C and run till it's done. So let's look at A, B, and C and how they're going to do. Remember, they run for 100 time units each. So if you think about time, it's like this. So A starts at 0, runs till 100. B starts at 100, point whatever, finishes at 200, and then C starts at 200 and ends at 300. Pretty simple. And so this is kind of a visualization of that. It's not a very fancy visualization. It's actually a name for this sort of timeline visualization. It's called a Gantt chart. And somebody, amazingly, if you were alive like in the early era of anything, you get to make something up, put your name on it, and then people are stuck calling the most basic, obvious idea your thing. And that's true with this type of chart. So So anyway, let's compute the turnaround time t for each of these. What's the turnaround time of A? It's 100, right? It's the time that ended, which is 100 minus the time that arrived, 0, so it's 100. The turnaround time of B is 200, right? Because it started at the same time but finished later. And then the turnaround time of C is, I bet you can guess this one, it's 300. And then you can, of course, compute, we'll often do this, we'll say what's the average turnaround time of this entire scheduling policy across this entire set of jobs. And you can see in this case it's 200 by using our tricky friend, math. We'll sometimes use math in this class. We won't ever do anything very complicated, like maybe algebra. So if you have gotten through the 8th grade, you should be good in here. The system stuff is hard enough. We don't need to confuse it with a bunch of complicated mathematics. So that's turnaround time. So now what we're going to do is we're going to go back to our assumptions and start to relax them. We know these are all kind of unrealistic. So let's relax some of them and see if we can build a more realistic scheduler. So the first thing we're going to relax is that all jobs have the same length, runtime. So let's pick, okay, we have A, B, and C. And we have different runtimes for them now, not the same. But let's say we were mean. Now, it's going to be good to get in the mindset of being a mean person, because sometimes we have to think adversarially about the operating system. We have to think how to do things so that we kind of break what the OS wants. We want to make it bad, and then by thinking about it adversarially, we will be able to build a more robust mechanism that can deal with those sort of adversarial conditions. That's certainly a good paranoid mindset to get in, and it just turns out to a good way to think about a lot of things that we're looking at in this class. So let's say I wanted to create a workload that's it's going to run A, B, and C in that order, okay? Because let's say they all arrive at the same time, and we just say A runs before B, runs before C. But we've relaxed this assumption that all jobs have the same runtime, which means they no longer do. Which means we can pick the runtimes of A, B, and C. So how would we pick the runtimes of A, B, and C given our FIFO algorithm, which we know is running, so that FIFO doesn't seem to do that well for average turnaround time? Why don't you do this? Think about that for 30 seconds. Feel free to chat with somebody, and then I will try to rein you back in, and we will answer it together. All right, why don't we come back? There's a question or an answer? Question and an answer. So are you answering your own question? Okay, question for me and then an answer to this. Yeah, that's right. That's a great question. So already there's some other assumptions we're making, which I didn't actually explicitly state. For example, that right now we're just saying we're going to run one job to completion, then the next, and we're assuming that there's essentially a 0 time to switch between running, say, A to B. That context switch, which we talked about as a mechanistic thing, is not free. And certainly, the more you switch, let's say you rapidly switch between processes, at some point you'd spend all your time switching. So for now, we're just assuming that it's free, and it does. Oh my God. Sorry. That's how excited I got. For those of you listening in the future, there's a technical difficulty at this point of the lecture. We won't say what it was. It'll be mysterious. People will talk about it in the future. So we're assuming that there's a zero cost context switch right now. We can later talk about a real cost there. And there are a bunch of costs, actually. If you think about the cost of context switching, not only is there the jumping into the kernel and then switching context and then jumping back into the kernel, what else would run more slowly if we were switching back and forth a lot? Why else would the computer run more slowly? Yeah. Yeah, like caching, right? Perfect. If the hardware, what is hardware really good at? Hardware is really good at kind of like doing the same thing over and over again. So if you switch to doing something else that's completely different, all the state that's built up, the implicit state that's built up inside the processor has to kind of get thrown out if you know how hardware caches work. And so switching back and forth has an explicit cost. It takes time to switch. But then it also has this implicit cost. You just kind of run more slowly when you're first running. And then eventually you run quickly again. So good question. Just assuming a zero cost. Maybe someone else then can answer. What's a kind of setup here that would be poor for FIFO? What's a set of runtimes? Yeah, in the back. Yeah. Yeah, let's make this like 1 billion. No, let's just make it like 100, and these are like 10. 100 time units. Sounds very menacing. And of course, why that looks terrible from a turnaround time perspective is A runs for a long time, and then B runs, and then C runs. And if you look at the turnaround times then, you know, this is 100. For B, it's 110. For C, it's 120. And the average turnaround, as you can see, is 110. But if we instead had run B, and then run C, and then run A, notice we're not finishing the work any sooner. If our metric was the total completion time of the job, of all the jobs, switching the order doesn't make any difference at all. But if our metric is the average turnaround, then you can see here that the average turnaround is 120 plus 20 plus 10 is 150 over 3. So T average equals 50. So a much more responsive, quicker system, and people started thinking about this when they started thinking about interactivity. Like you're sitting at a desktop and you want to get an answer right away. So generally what we want to do is our goal should be, is to schedule the shortest job first. And this is our second policy, shortest job first. And we call that SJF. So that's a kind of a scheduling principle, that when you have a bunch of work to do, if you care about the response time of each, figure out what the shortest ones are, and then run those first. You see this all the time in the real world too. Where do you see this? Yeah, classic example is a grocery store with the kind of short checkout line, right, where you 10 items or less. That's realizing that not all jobs are equivalent. Some you have less work to do as opposed to, somebody, getting, 3 months worth of groceries or something like that. If you're behind them, you get angry. You wish you had gone over to the 10 items or less checkout center. It's just a classic example, and that's where people start thinking about these things. Scheduling, as I say, is ubiquitous. It's in everything. Okay, so now we have shortest job first, but we want to generalize again. So let's go back to our assumptions. We assume that all the jobs arrive at the same time, but they might not. So let's relax that. And let's relax it so we get to cross it out. Pretty exciting. And so what we're going to do now is just say what happens if a job arrives later. let's say we have A. A arrived, and A normally would run for a very long time. So A arrived here. But then, just a little bit into its running, B arrives. And B's runtime is short. Let's say it's 10. So if we just kind of went with our existing schedule, what we would do is we'd punt B out to here, and you could see that this huge amount of time would be spent waiting, and then it would run later, and the system wouldn't feel that responsive. So it's kind of a generalization. Now, I guess I should say about shortest job first before we move on from it. Shortest job first, given the assumptions that we have, a set of jobs all arrive at the same time of different run times. Shortest job first is going to give you the lowest average turnaround time, period. You can prove it if you did. If it were a theory class, we would prove it. This isn't a theory class, so we just assert things and hope that nobody disproves them. But no, it's been proven by others. So this is just the best we can do given those assumptions. But now we're changing the assumption, and so we're going to have to slightly think about it a little bit more differently. How do we handle this job here? Well, what do you think? What's an intuition? Or what should you do when B comes in at this point? A has run for a while, and then B comes in. Which should we run? Should we keep running A, or should we run B? How do we make that decision? Who knows? Who has a sense of it? Yeah. Yeah, great. If you didn't hear that, basically the generalization of shortest job first that takes into account the jobs run at different times is basically shortest time to completion first, or STCF. And what shortest time to completion first does is basically, let's say A was this long, and then let's say B was this long. If B arrives, anywhere kind of in this time frame, then when B arrives, if it arrives from here to here, then what's remaining of A is longer than B's runtime, so we should run B. But if B arrives like in this last part here, where A's remaining time is less than what B is, and then we would run B. Then we would run A instead. So basically, when something arrives, you look at what's running, you compare what time it has left to the time of the new job, and then you run whichever of those is shortest. Yeah. Again, we're assuming, yes, perfect. We're still assuming that we know this completely unrealistic thing. Not always unrealistic. Let's be a little careful about that. There are some circumstances. Let's say somebody hires you at a real-time company that's building some embedded, Internet of Things device, and let's say you know exactly a lot of detail about the programs that run on that device because you've written all of them yourself or your company has. You might have knowledge of how long certain jobs run. And in that kind of real-time world, you might be able to say, oh, I know exactly I should run this, not this, because I know all the runtimes. In a general purpose OS, where you're just sitting there typing commands away, we generally don't know. So it really depends on the environment, but we'll always, in this class, kind of focus on the general purpose OS rather than the more constrained real-time scenario. So that's shortest time to completion first. But, and, we have this new thing that we're doing. We're preempting a job. So in some cases, to preempt means what we're doing is we're stopping, the existing one and starting a different one. So preemption just means that. It just means that basic mechanism that we were talking about. We have the ability to stop a job, a process, and run another one that's preempting the process. It's also that context switching. Those are all talking about the same things. So some early schedulers weren't preemptive, which means they always just, whenever they started running something, they ran it to completion. Here we're, of course, going to get towards a more general mechanism where we're going to use preemption in order to do the things that we want to do. Okay, so that sounds good. We have shortest time to completion. But now what we're going to do is we're going to introduce a new metric. So essentially we're relaxing the assumption, the last assumption we made, that the turnaround time was the only metric that mattered. And this will be the last thing we talk about before taking a break. The new metric is what is called response time. And we define this a little bit, I think, differently than sometimes you'll see in the research literature, which I'm sure you're all actively scouring, is, hey, can I read another? I get these requests from you almost every day, like, can I get another paper about CPU scheduling from the 1960s? I'd love to read those. Okay, so nobody has ever sent me a mail like that. But if you did, what I would tell you is that there are other metrics other than turnaround time, and one of those metrics is response time, and that we define it maybe a little differently than some. Some define it like this. They say it's the time until, say, the process generates a response of some kind to whatever, it's like it prints a message or something like that. I think that's really sloppy because it really depends on the program when it's going to generate a response. It might start running for a long time before printing hello, or it might immediately print hello. Or it might not even print hello because it's a very rude user process that doesn't even say hello to you. All are possible. So whatever it is, that's how some define it. I'm going to define it more simply, which is, so our definition is very simply like the time that the process first runs minus the time that it arrives. So basically, how long it waits at first until running. So that's just going to be our simple definition of response time. Just make sure I get that for you, our definition of response time. Now, we said shortest job first was optimal for what it's in its constraint scenario, and then its generalization actually, shortest time to completion first. That's optimal, assuming jobs arrive at different times and you know their run times. But how do these do for response time? Well, let's say you have 3 jobs arrive, A, B, and C, and you schedule A, which is shorter than B, which is shorter than C. So this looks like a shortest job first schedule. But the response time, the real responsiveness of the system actually isn't that great because A runs right away, but B has to wait a long time, and C has to wait a really long time before it runs at all. So the response time of B is this, like this is B's response time, and then the response time of C is this response time. So if we want a policy that uses all of our mechanisms in order to minimize response time, what would that policy look like? Let's say we want to minimize response time. What policy would we invent? What would we do? We have CPU mechanisms. We can preempt things. What would we do? Yeah. Yeah, and let's say they all arrive at the same time. Then what would we do? Yeah, perfect. Perfect. Yeah, what you would do if you want to minimize response time is you run one for a little bit, then you switch to another one, run that for a little bit, switch to another one, run that for a little bit, and then kind of keep maybe cycling through them. That's another policy that people do. It's called round-robin scheduling. And instead of running A to completion and B to completion and C to completion like we see up here, what we do is we run a little slice of A, then we run a little slice of B, then we run a little slice of B, C, and then we go back to A, B, C, etc. And the length of time that we run one of these jobs, sometimes we call that a quantum for various reasons, or we sometimes call it a time slice. And you can think of this as some multiple of our timer interrupt period. Right? We have a timer interrupt going off, say, every few milliseconds. And every few milliseconds, we can decide, do we want to switch to some other job or keep running the same job? So if we might have a time slice might be, say, 10 milliseconds, which means this length of time is 10 milliseconds. That means, our timer interrupt must be going off, certainly could be going off every 10 milliseconds, but it could be going off every 5 or every 1, and then we just decide to wait through some number of timer interrupts. Now, a natural thing with round robin is we have this trade-off, that if we have really short time slices, and that's another new term, a time slice or a quantum. If we have really short time slices, we have better response time. But as we talked about, we might have high context switch overheads. Right? If you're constantly switching at a very fine granularity between one job or the next, at some point the system's gonna run more slowly. You're spending all your time switching. You're not letting the jobs just run. Longer time slices have the opposite, right? Longer time slices have the effect of slightly worse response time, but more efficient. Fewer context switches. So there's some trade-off, some length of time, which is kind of the best you can do. So what do we have now? Actually, what we have now are a bunch of ideas. We have the idea that we generally like to do something like shortest job first, or shortest time to completion first, but we don't know job lengths. And we'd like to care about response time because that seems like a nice thing, not just turnaround. So how do you build a real scheduler that takes into account all these things and achieves all those goals kind of at once? That will remain a mystery for today, but we will pick that up actually next time. So we're not done with class entirely. Now we're just going to do a little homework together after a break, but there's a few questions first. Yes? That's a good question. So the question, if you couldn't hear it, or just didn't hear it on the mic in the future, which will now be a running theme, we will constantly be imagining the future in this class. If nothing else, we'll have a record of all of our predictions of what is definitely not going to happen on the Earth. So the question is really about I talked about turnaround time, I talked about response time, what do modern operating systems really care about? I'm going to slightly defer that question because what we'll do at the end of talking about scheduling, which we'll actually do next time, is we'll talk a little bit about real Linux schedulers and real schedulers in other systems, and then we'll talk about all the things they try to balance. Basically, depending on the system, they value different things. For example, sometimes in a shared environment like the cloud, you really care about things like fairness. That's like your first thing that you care about. You care about a different metric that we haven't even talked about, which is, hey, am I getting my share of this CPU or not? Because I'm paying for half of it, but somehow the scheduler is giving 60% of it to the other user who I'm sharing the CPU with. So that would be kind of a big thing in cloud environments. In other environments, different things matter. And a lot of schedulers actually, some schedulers, like going back to the old Solaris scheduler, that's built to be super configurable. So you can kind of put in a few different numbers here and there, and then have it behave completely differently based on the workload that you're interested in. But we'll talk about that more next time. That's a good question. And I'll try to, at the end of each kind of major section, kind of connect it back from concepts to what's going on in the real world. So we'll do that at a few different points in class. Any other questions? Yeah?
I have a follow-up to that.
Yeah.
Is that kind of related to settings that you use in modern operating systems? Like, do you want to prioritize performance over battery costs?
Oh yeah, sure, it could be. But that also, so the question is about how you, comparing performance and battery, battery usage and things like that. But that also will relate to not just OS scheduling, but actually hardware settings. About are you running like the hardware at full throttle, or are you kind of running slower in order to conserve battery? So that might relate more to hardware settings, but it could have an OS scheduling flavor too. Other questions before break? Glorious break number 2. Yeah, who wants to stand between us and the glorious break? Nobody. Okay, break number 2. We'll do another 5 minutes, and then we're going to switch gears and just do some work together, which will be oh so fun.